This is section 8.8. Section 8.8 deals with catalytic hydrogenation reactions of alkenes. And what we mean by that is the addition of two hydrogen atoms across the CC double bond, as shown here. So in this reaction, if you have an alkene under hydrogen gas pressure in the presence of platinum metal, you can fully reduce or add in hydrogens to the CC double bond in 100% yield. These are very good reactions that are run, and they're called heterogeneous catalysis because platinum is a metal that is not in the same phase as the other reactants. It's a solid, the alkene is a liquid, and the hydrogen is a gas. The platinum, the catalyst, is in a different phase, and because it is in a different phase than the main substrate, we call that a heterogeneous catalysis reaction. Hydrogenation does not have to be heterogeneous, but in this case, it is. And there's stereospecificity here in the catalytic hydrogenation using platinum because, again, there's a top face of the alkene and a bottom face of the alkene. And you have syn addition of the two hydrogens. There's a top face and a bottom face of the alkene, and you have syn addition of the two hydrogens either to the top face or the bottom face. And the reason why this is, before we get into the reason why, let's show something else interesting. This cyclohexene can have 4 different enantiomers. One set of enantiomers that results from syn addition, and one set that results from anti-addition. In this case, in platinum catalyzed hydrogenation, you only get the syn enantiomers. So, like, say for instance, with this enantiomer, the anti-enantiomer would be one where this ethyl group was up instead of back. But in this case, you can't form that one. You only form either the both back or the both forward enantiomers. And that's because of syn addition. And the reason why it's syn addition instead of trans addition or anti-addition is because you can think of the platinum metal, its surface, as kind of just like a shape, like a sum polygon. In this case, this is like a cuboid rectangle. And on that shape, on the surface of it, are all of these hydrides, because platinum is very good at turning hydrogen into it's very good at turning hydrogen gas into individual hydrogen atoms bonded to the metal surface. And with those hydrogen atoms bonded to the metal surface, if the alkene comes close enough to the surface, there happens to be a reaction where the hydrogen attaches itself to the alkene at the same time that the alkene bonds to the metal on the surface. And with this bonded alkyl metal complex, then a hydrogen can attack that carbon atom, resulting in a syn addition. And this is how platinum catalyzed hydrogenation reactions occur. And the key is that syn addition is totally due to the metal surface. The metal is a stationary phase, and the reaction happens totally on one face of the molecule. As I said, we don't have to have heterogeneous catalysis. We can have what's called homogeneous catalysis, where the catalyst is actually in the same phase of the reaction as the reactant. So in this case, you have a cycloalkene, as we saw before, reacting with hydrogen gas under pressure, but this time the catalyst is this rhodium catalyst that is also dissolved in the reaction mixture. And with the catalyst also dissolved in the presence of hydrogen, you also make a syn addition product. However, there's no real way to control which isomer you get, whether that's forward or back, because there's no chiral part of this molecule that's forcing selection of one enantiomer over the other. For that, we would have to have what's called asymmetric or enantioselective catalysis to really be able to increase the selectivity for one enantiomer over another, potentially. And this has been a fairly new part of chemistry in the past 40 or 50 years or so, which now is fairly new. But there are two very famous types approaches to do this. And these two are shown here. In general, the idea is that you need some type of chiral ligand that forces the molecules when they attach to the metal here and here to adopt some chiral configuration, so that instead of only having a racemic mixture of enantiomers, you select for one over the other. Remember, both of these types of ligands, this one and this one, have chirality. This phosphorus ligand has chirality using the wedge dash structure like you're used to seeing, but this binap or binaphthyridine type ligand has axial chirality. That's why these sections of the molecule are in wedges, because you should think of this coming out of the page and this part coming out as well. So the ruthenium here also has a chiral environment, just like this rhodium does. And with a chiral ligand, it turns out you can perform very good enantioselective reactions. You can do hydrogenation reactions, such as on this vinyl alcohol in the presence of hydrogen gas and the ruthenium binap catalyst, to fully reduce it in very good enantiomeric excess, 95% of just this one enantiomer. Notice how the methyl is pointed up, and we don't talk about the methyl pointed down version. But as was the case with a few other reactions that we saw, alkenes are not the only molecules to undergo hydrogenation reactions. Alkynes also undergo hydrogenation reactions, and details of those reactions are found in pages 411 and 412 of your book in Chapter 9. If you have an alkyne like this one, and you submit it to heterogeneous catalytic hydrogenation, just as we saw before, with two equivalents of gas molecules now, you fully reduce the alkyne all the way to the alkane. You can't really control it because the reaction is so good. However, you can stop the reaction at the alkene if instead of platinum, you used a poisoned palladium catalyst called Lindlar's catalyst. This palladium has been poisoned with a little bit of calcium carbonate and lead oxide. And if you do that, it has just enough power to hydrogenate an alkyne to an alkene, but not to the alkane. And what's very interesting about this reaction is because we're talking about syn addition on the same face of the alkyne, you preferentially make the cis alkene only. The trans alkene does not get formed here due to the facial nature of this reaction. So this has been section 8.8 and alkyne hydrogenation.